Hello everyone, welcome to Code Forces contest. Goodbye 2024. 2025 is near the last Code Forces contest of the year, and this will be my last video of the year as well. So let's get started. So we'll solve few questions from here. So question A, tender carpenter. So in this question, it's a pretty simple question. In this question, question A, tender carpenter. In this question, we are given n integers a1, a2 up to an, and we have to determine that whether we can partition these in more than one way, such that each partition can correspond to sides of a degenerate triangle. By degenerate triangle, which means it satisfies the strict triangular inequality. So it is pretty simple. So one feasible partition is having every element separated. So that is one thing, having every element separated. Now we have to check whether we can club any two of these together. So in order to do that, the simple condition is if ai and ai plus 1 can be partitioned together, the only condition should be, suppose ai is less than ai plus 1, then the only condition that is required is ai uh, uh, ai plus 1 should be at most rather strictly less than 2 times ai. This is all that you need to check. So, and if any of such ai exists, so we'll return yes, else we'll return no. So this was the first question. Moving on to the next question. Outstanding impressionist. In this question, there is this painter guy Eric who has some impression recorded as W1, W2 up to WN, and he just remembers each of the impressions lie between the integers uh, li, and each impression wi is between the interval li and ri, something like this: L2 less than R2 and Ln less than Rn, something like this. And what we have to determine in this question is, for each impression we have to determine whether that impression will be unique. So for example, let me take the test case. Say L1 R1 is 1 and 2. Suppose we have three impressions: 1 2 2 2 and 2 2, something like this. So if we set W1 so if L1 R1 is 1 or 2, L2 R2 is 2 and 2, and L3 R3 is 2 and 2. So in this case, if we can set L1, we can set W1 to 1 and other are forced to 2. In this case, W1 will be something which is not equal to W2 and W3, so this can be a unique thing. But in case of W2, we have to force it to 2, and W3 is also supposed to be forced to 3. So in this case, these two cannot be unique. So our answer would be 1 0 0. Essentially, all those W's which we can assign unique integer values are supposed to named as 1, else they are supposed to basically we should return 1 at those places and 0 at others. So how do we go around solving the question? So one simple observation is if for a given so if there are so the only problem which we'll ever face in this type of question is in this question particularly, is that if we have intervals of type ai comma ai, or rather something like 5 comma 5, 6 comma 6, 7 comma 7, and something like 5 comma 7. So in this case, this interval will be set to 5, we don't have choice. This will be set to 6, we have no choice, and this will be set to 7, we don't have choice. But what about 5 7? This will also be set to now, since we cannot set we had to set something between among 5 6 and 7, but none of them will be unique because that has been already taken by someone else. So how we'll go on solving this question is, uh, first of all, we'll look at all the w's whose feasible range is a single integer, and we'll store them. We'll store all those uh, ranges which are of all those feasible range of single integers in a dictionary, and if their count is greater than 1, which means they cannot be assigned an unique value. So for example, in the about test case, in the example test case, we have a 1 1 and 1 1. So now, so in our dictionary or in our map, we'll store that the 1, like the feasible range is 1 is for 2 entries. So, and now when we are writing the filling out the answer array, if we encounter 1, and its count is greater than 1 in our dictionary, so uh, we say that it's not possible to assign unique entry. So this was it. Now what about, now this is one part, and how to handle the entries which are not, how to handle the ranges which are not single entries, so something like 1 comma 3. How do we handle it? For that, we need to check whether 1 1 exists, 2 2 exists, and 3 3 exists. And now the thing is, we need to answer this in constant time, or say efficiently, because the inputs on a larger input size, we might get a time limit exceeded error. So since we know that the values of li and ri are at most 2 times n, so we can use the concept of prefix sum array. And what we'll essentially do is, once we have enumerated all the entries which are of this form, basically single feasible region entries, what we'll do, we'll iterate over it, and we'll have this array of a prefix sum array of size 2 into n, 2 into n plus 2, of size 2 into n. And what we are going to do is, wherever we have a single entry guy, we'll increment that position with 1. So for example, in this, I'll run through an example test case. So for example, take 4 5 4 4 and 5 5. First, so initially our answer array should be initialized to -1. Now 4 4 and 5 5 are in our dictionary, and they each appear only once. And then we have our prefix sum array. Then we have our prefix sum array. 1 2 3 4 5. Okay, now we have our prefix sum array. Now what we are going to do here is, since 4 and 5 occur only once, it is okay for us. Since they occur only once, we can have them give them a unique value. But now think about, now we have to take care of this interval 4 comma 5. So when we so how do we create the prefix sum array? So when if the value of, so 4 belongs in our dictionary, will set its value to 1. 5 belongs in our dictionary, will set its value to 1, and we'll take a prefix sum of this array. So we'll get 1 and 2. And now what we do, whenever we have to check for the entry, whenever we have to check for the interval 4 comma say I comma j, then essentially we'll take the prefix sum of the array from we'll basically take prefix sum of this array, and we'll query the sum between array of I to j. We'll basically query this interval for the sum, and if this is equal to j minus I plus 1, which means that everything, so everything include from I to j is set to 1, which means all the entries are blocked. We cannot have any unique value to it. So for example, if we have 6 6 9, and everything in our and we had intervals like 6 6 7 7 8 8 9 9. So what will happen? So our prefix sum will look like our prefix sum will look like at from 6 to 9 will look like this, and before that it might look like 0. And then once we take the query the prefix sum from 6 to 9, we'll get the value as 4. We'll get the value as 4. And since 9 minus 6 plus 1 equals to 4, this will tell us that every entry from 6 to 9 is blocked. So this particular entry cannot have this particular interval cannot have any unique entry. So that is how we will handle this question. So basically you need to use the concept of prefix sum, because Li and Ri's were bounded by n. So moving on to the next question, B. V. Cheng Stargazer. B. V. Cheng Stargazer. So in this question, there are n stars. This iris is looking at stars. There are n stars, and what essentially is happening is, if n is odd, what we'll do, if n is odd, she will take the middlemost element, that is n plus 1 by 2th element, and she will add it. So initially her luck is 0. She'll increment her luck by n plus 1 by 2th element, and now she will split the remaining intervals into into two parts, that is from 1 to, if we assume this as mid, then from 1 to mid minus 1 will be a separate interval, and from mid plus 1 to n it will be another interval, and she will recursively see stars from 1 to mid and mid 1 to mid minus 1 and mid plus 1 to n. But if n was even, she will essentially she won't increase her luck. She will just observe from 1 to n by 2, and from n by 2 to n by 2 plus 1 to n. She will just split it. She won't add luck. So for example, I will have an example ran over here. So suppose suppose n equals to 7. Okay, so initially she will observe star 1 2 3 4 5 6 7. Now since 7 is odd number, so she will look at the middle element. So middle element is 4. So her luck is increased by so her luck is now 4, and now these are the two separate intervals she has. Note that we also have another integer k, which tells her laziness, which means if any intervals is strictly less than k, she won't observe those intervals. So in this case, both the intervals that she have created are of size 3, which is greater than 2. Now she will observe each of these intervals. So she'll look at 1 2 3, and now since this length is odd, she will observe she will add luck of 2 to her. And since the interval later created of size 1, so she won't observe those further. And recursively on the other end, after looking at 5 6 7 6, she will add her luck by 6, and the interval created 5 and 7 are of size 1, which is strictly less than 2, so she won't look further, and she's done with her stargazing, and so her final luck will be 12. So we had to return this. So now, okay, we know what she's going to do, but now how are we supposed to, how will we solve this question? So one thing that you might have observed, that after every like this question is there is some sort of symmetry in this question. By symmetry I mean, if suppose we have an interval L2R, when we pick the mid element, there are equal number of element in the left from the interval L to mid minus 1, and from mid plus 1 to R. There are equal number of elements, and since we have equal number of elements, the division there will be some sort of symmetry. By symmetry, I mean same number of elements, same number of stars will be picked from both ends, but there will be certain difference in the uh, same number of elements will be picked from both sides, but there will be difference. The luck value will be different. But then I want to claim that we can predict this luck value, and we'll solve this in log n time. So let's see how we'll do it. So let's start. So let us keep track of the following values with us. So for example, when n equals to 7, we check if n is divisible by basically this will be our length, and we'll check if this length is while this length is greater than equal to k. What we are going to do, if if this length is divisible by 0, then we will then we will store we'll maintain a vector. And if this is divisible by 2, not 0, if this is divisible by 2, we'll push 0 comma the length into our vector. If not, we'll push 1 comma the length of this interval into our vector, and we'll maintain it throughout. So basically, since we are divide, and then after that we'll update n, we'll replace n by n with n is equal to n divided by 2. So we'll replace n by that, and we'll store this these values somewhere. And now I will come to it, how are we going to use this value. So I'll just take an example. So for n is equal to 7, so since 7 is not divisible by 2, so we'll have 1 comma 7 in our entry, and then 7 divided by 2 is 3, and 3 is still again not divisible by 2, so we'll have 1 comma 3 in our this thing. Okay, now we have this. So now we have these two elements, and now we'll traverse them in reverse order. And now what we are going to do, so observe this carefully. So now we start with initial luck value as 0, and we maintain another integer called digit, which is initially set to 0. Now we start from bottom. So look at 1 comma 3. 1 comma 3 means that from interval 1 to 3, this is of odd size, which means its center element we should be taking into account. So in this case we'll increase our luck by middle of these element. Luck plus is equal to mid of 3, and by mid of 3 I mean I'll just increment it 1 and divide by 2, something like this. Okay, and we'll increase the number of digits by 1. I shouldn't use the word digits, I should use something better, like maybe number of numbers. So it was 0, and I will increase the number of nums by 1. Okay, so now we have calculated, we have taken into account this part of the answer. And now see, what I wanted to claim, that there is some sort of symmetry at every part of this question. So what I mean by that is, if when we divide the interval of 1 to 7 at 4, so 1 2 3 becomes one side, and 5 6 7 goes on the other side. So if we are picking 2 from here, we know that correspondingly we are picking an element 6 from there, and we just need to know how far the element is from here. So since the interval above this, like the interval above 3 is this 7 interval, so this interval was of odd length. Since this interval was of odd length, the corresponding element will be at a distance 3 plus 1 on the other side. Correct? By this, what I mean is, so because we are picking 1 2 3 4 and 5 6 7, so because of so we know that this interval that we are looking at currently is of size 3. There will be an element in the center, and there will be another interval of size 3. So from here to here you need to so if this one wasn't there, then the corresponding element would just be 3 elements further. But since this center guy is there 4, so we'll have a 1 extra, we'll have to add 1. So we just see that if the next element has bigger size, uh, if the next element is of odd size, we'll increment to find the corresponding element, will increment by 1. So finally our luck value would be, we'll update this by luck is equal to 2 into luck, because whatever elements are here we want them here also. So we'll double it, and now look at the number of digits we had here. So suppose look at the number of digits we had here in this part. So we have it stored as nums, nums or whatever num, that many digits into the difference that we just saw, that is 3 plus 1 4. So that will be this number plus 1. Okay, so this will be our final luck till this point. Okay, and then for the final limit we'll just check if this dude is odd or not. If this is odd, then we'll add the centermost element. I'll take another example to make it clear. So suppose we have the interval suppose we had the interval 14 comma 2. So 14 will be splitted as 1 to 7 and 8 to 14. So in our entry we'll put 0 comma 14. Now 1 comma 7 is again splitted as 1 comma 7, and 1 comma 7 is splitted as 1 comma 7, and as 1 comma 3 and 5 comma 7, and it's further splitted as 1 comma 3. So initially our luck as luck was 0 and num was 0. Okay, then we look at this element. So then our luck becomes 2 and our number becomes 1. Okay, and now when you have to update it, we'll make our luck value equal to this, and after that we have to double the value of nums also. Nums is equal to, because the number of digits we have here will be equal to the number of digits we had here. So after that num will become twice, but before that, to update num, the luck will be 2 into luck, that is 2, plus nums, we had 1 num, into 3 plus 1, that is 4. So this will become 8. So we have taken care of this part. Okay, and now after this we'll move on to the next digit, 1 comma 7. Since this is 1, the number of nums will increase to 3, and their center element will be added to this. So we'll get 12 over here, and now we have to do the following update. So the numbers will become twice, that will be equal to 6, but 12 become 2 into 12 plus initially we had 3 plus nums, we had we have 3 nums, so 3 into 7 plus 1. So 3 8s are 24, 24 plus 24, this will become 48, and this will become 48, and the answer for, and then we move on to this digit. Now 0 comma 14, we don't need to pick anything because there was nothing picked, so the 48 should be our answer. So that is how we'll go around it. So this was third question, and moving on to the final question. Refined product optimality. So in this question, we are given array A, array B, and what we have to do is we have to find the value of P, that is P is equal to product of from I equals to 1 to n min of AI comma BI after any possible rearrangement of B, after any possible rearrangement of BI. Okay. Now this question is not just simple. We will have q queries, and we had to answer, we had to output for every test case we have to output q plus 1 values. That is so the query will be of the type 0 comma x if sorry, not 0, o comma x, o comma x. If o equals to 1, then the element ax will be incremented by 1. If o is equal to 2, then the element bx will be incremented by 1. Okay, and for every modification we have to answer this query. Now the thing is how do we do it? So, and we have to maximize this value p. So to maximize this, it is, if suppose we had no queries, so the smart way to maximize is sort a, sort b, and find the value of min of so over all the integers. You essentially take product of min of ai comma bi over all I equals to 1 to n. So this is the way to do it. But now the thing is, you will be getting queries where some values will be changed, and now the thing is, how do you handle this? So in order to handle this, what you should be doing is, so in order to handle this, what you're going to do, so we know that so essentially we maintain a copy of A, we maintain a copy of B, and we sort this copy, and whenever we get a query over here, whenever we get a query in this whenever we get a query, we go and we search the we find which element is being changed in the original copy, and in the sorted copy we go to that element. In the sorted copy we search that element, and suppose in the sorted version ai is changing. Suppose in this so suppose in the sorted copy ai is changing. Suppose this value is changing. So so we are only incrementing the values and incrementing the values by 1. So at most what is the worst that could happen, that ai and ai plus 1 could be swapped, and if bi is increased, then bi and bi plus 1 is swapped. Only these things can happen. So what we can do, we can initially sort both these array and find the value of this p product. Okay, and now we just know that only these values can change. Then what we can do, if we basically divide, if we for every query we find where does the particular index lie in, using binary search we can find in the sorted copy where does the particular value, at what index does the particular value lie, and then divide pi by ai min of ai comma bi times min of ai plus 1 comma bi plus 1. We divide p by that, and after that we increment ai by 1 and new ai by 1 and check if these two can be, then and after that we can check if these two can be swapped. If these two we check if these two can be swapped, and after that we multiply p again by min of ai comma bi and min of ai plus 1 comma bi plus 1. We do that and essentially we can answer every query in log n time. So the overall running time is n log n plus q log n. So that's it for today. Thank you.